All right, before we get on to more chapter 3 stuff, I briefly wanted to make a couple notes about this. First, again, this David Ortiz data was a very weak positive relationship, but a positive relationship nonetheless. When we get later in the book, we can actually test, based on this value of r squared, whether it's what's called a statistically significant positive relationship. Did this just occur by chance, or is David Ortiz more likely in future seasons then, although he probably doesn't have any left, to get a lower batting average and hits for more power? Okay? The other thing I want to point out is the slope is very small here. Can you zoom in on that? Can you guys see this very well in the back? Can you see that at all? It says 7.304 e negative 4. That's the slope. It's times x. 7.304 e negative 4 is the same as scientific notation 7.304 times 10 to the negative 4th power. And what it means is, with the decimal, you need to move it 4 spots to the left when you write it in the ordinary notation, which would in effect have 3 zeros. 0.0007304 is the slope. Okay, in case you encountered that. How would you use this again if you wanted to, for example, for next season, predict what David Ortiz's batting average would be based on a certain number of home runs, say 30 home runs? You'd want to replace x with 30, so multiply this by 30, and then add the y-intercept, which is 0.261. If he hits 30 home runs, your prediction for his average would be 283. Again, will that happen? Probably not. That's just your best guess in the absence of other information. Okay? So you should be able to use formulas as well, like this. All right, on to chapter 3. There's a lot of things here to go over in a short amount of time. I think it's probably best if you don't take notes, except maybe here or there, and really focus on listening to what I say. Okay, thinking as well as you can. Get yourself to think during the time we have here. Okay, and then if you feel like going back and taking notes based on putting the PowerPoint on Moodle, then go ahead and do that. Read the book as well, study the book, look at their examples. Lots of pretty important ideas here to go over in a short amount of time. First off, a lot of terms here. An observational study. We're talking about gathering data here, is the big picture. There's two main ways of gathering data, observation versus experiment. In an observational study, you observe individuals and their characteristics, and you measure variables of interest, but you don't attempt to influence their responses. For example, you might be observing the effect of smoking on lung cancer. You've got lots of people. You find out if they smoke or not, and if they do smoke, how much do they smoke. And you keep track of other things like their sex and their age and where they live and that kind of thing. And again, you keep track of whether they got lung cancer, or if they do have lung cancer, how bad is it, and does it progress over time, does it get better? You're observing what happens, okay? You're not attempting to cause these people to get cancer. That would be immoral. You're not attempting to force them to smoke. That would be immoral. You're not even trying to force them to not smoke. You might say that's immoral too. So you're just observing what happens. There are problems with that, however, because there are other variables that you can't control for, like age, for example, like general health. Do they exercise? How do they eat? You can't control for those other things. They are what they are. So you're just observing. In an experiment, you are deliberately imposing some treatment, it's called, on individuals and observing their responses. For example, when you are testing a new drug, this is the main example people talk about in this kind of situation, when you're testing a new drug and trying to decide, is it effective and is it dangerous or not, you have to do experiments if you want your data to be valid. And for the FDA, for example, Food and Drug Administration, to approve you in the United States, to approve your drug for sale. Okay, I don't know exactly what their standards are, but there are some standards for proof of effectiveness and proof of safety. Actually, I think they're more concerned about safety than they are about effectiveness. So that's one of the main examples we'll think about with experiments. We'll think about other examples as well. More terminology. Two variables are said to be confounded when their effects on a response variable can't be distinguished from each other. People who get lung cancer, is it caused by their smoking? Or is it caused by their age? Or is it caused by their diet? Or their exercise patterns? Or even their genes? Genes, people think, doctors often think can cause cancer. They cause lung cancer? I don't know. I'm not an expert. It's a possibility. That can be a factor. All those variables could conceivably cause cancer. And so how do you know for any particular person what was the true cause of cancer? Or what was the most likely cause of cancer? Their effects on the response variable of the person's health in terms of do they have cancer or not are mixed up. You can't tell, especially within an observational setting. They do experiments on, for example, mice in controlled setting. You know, take a bunch of male mice of the same age and the same diet and the same general health and expose them to cigarette smoke, some of them, and others to a placebo smoke, not really a smoke, and see, do the ones who get exposed to the cigarette smoke develop cancer more than the ones who don't. That would be more of a controlled experiment. You can control for those other factors. The variables are not confounded that way. So the example is what I already just mentioned. Okay? More terminology. Not sure why I put these on the same slide as confounding variables. When you're doing a statistical study, the entire group of individuals you want to know information about is called the population. Okay, the whole population. Could be the population of a country, or a state, or even of a school like Bethel. Could be everybody in the whole world. It doesn't have to be people. You could be studying in a business setting what's an example? The population of products that you make. Some particular kind of product. Maybe like, I don't know, trying to think of something on the spot. A muffler on a car, for example. There's your product. Your company produces mufflers. That could be your population. All mufflers that you've ever produced, of a certain model, say. And you could even consider it to be the population to be all models, all that same model that you'll produce in the future that you haven't produced. And it can get even more abstract. You can even consider the population to be all of those mufflers that you did produce and will produce and could have produced, but you didn't. Okay, because you closed down the factory for the night. You could have kept it open and made more. There are lots of different ways to look at the population. It all kind of depends on your goal, how you want to look at it. It's not practical to typically get information about the entire population. Sometimes too time-consuming, sometimes too expensive, sometimes not really possible, because if it's all mufflers you could have made but didn't, then you can't, by definition, find information about the whole population. So you take what's called a sample. A sample is part of the population about which we actually collect information, used to draw conclusions, also called inferences, about the whole population. Right? Very, very fundamental terms in statistics. In fact, pretty much everything we do from now on is related to these things. We are sampling, and we're trying to say, based on how good our sampling method is, can we make conclusions about the whole population? That's pretty much what the rest of the class is about in lots of different situations. There are good ways to make samples, to take samples, and bad ways, and in-between ways. You don't want your design to be biased to systematically favor certain outcomes. For example, you don't want to ask in a survey leading questions or confusing questions. You don't want to give a treatment, like a new drug, to only a healthy group. and give the sicker people a placebo, which is a fake drug, not really a drug. It's inert, which means it doesn't react with your body chemistry. Right? You don't want to just give your drug to the healthy group, because that would tend to make your drug look better than it is, probably. It would bias that outcome. There are lots of different kinds of samples you can take. Something called a voluntary response sample is perhaps the easiest kind of sampling. For example, imagine you're doing a survey and you decide to put your survey questions in people's POs. What's going to happen? Lots of people are going to throw them away, right? Probably most of you, probably me even. I don't feel like answering that. Or especially phone calls. I don't want to answer your survey. Click. I guess I can't say click anymore. Then, okay. By the way, I still don't have a smartphone. I don't really want a smartphone.
Why not?
Take away too much time. Too busy as it is. I'd be playing games all the time.
So that's
Or too much.
not fun.
Well, it's fun, but I got lots of more important things to do. So, my wife will be glad to hear that I said that. Because I am tempted by games. All right. Anyway, coming back to voluntary response sampling, you know, people don't always answer. And the people who do answer probably are different in their opinions than the people who don't answer. Especially if it's like a political question. I want to let my opinion be known. Their opinions, people whose opinions are strong, tend to be different on average than people who don't respond. And so you're not getting the information you want. You're not getting information, good information about the whole population. The most simple and perhaps ideal for us way of sampling is called simple random sampling. However, just because it's simple doesn't mean it's really actually very easy to do. It could be costly, it could be time consuming, and even if it's not costly and time consuming, it is actually difficult to create what are called random samples, but it's an idea that we assume that we do a lot of the time. A simple random sample, or SRS of size n, consists of n individuals from a population chosen in such a way that every set of n individuals has an equal chance to be the sample actually selected. Kind of an abstract thing, thinking probabilistically by chance. You got some group of 10 people from a population of 1,000 people. If that group of 10 people has the same chance of being selected as every other group of 10 people, which would be a lot of groups of 10 people, then you would call it simple random sampling. How do you do simple random sampling? Okay, well, it's not perfect, but you can try to use the table of random digits in the back of the book like you did for today. We'll talk about that more at the end of class today. You can also try to use rand on a spreadsheet, though it's a bit tricky. I won't take the time to talk about that. That's something else you can try to do. There are other computerized random number generators that can help you create simple random samples, at least approximately. You can assume they're simple random samples. In all the theory that we do from chapter 4 and on, we're basically assuming we've got simple random samples, because it keeps the math a lot easier. If you do more complicated kinds of sampling, that can sometimes give you more information, something called stratified random sampling, for example. It gets more complicated. You have to think about the different strata, and if you want to think about everything together, the math becomes a lot more complicated. So we're trying to focus on the basic thing in here. So we assume simple random sampling. You do it in 2 steps. You give every individual a label, like for those ringtones, 0 through 9 were the labels you're supposed to give them. For 10 ringtones, you can use 0 through 9. No problem. And then you use a table. And your use of the table for that problem should have been very easy. You just went to line 101, and the first 2 digits were different, so you could use those for your numbers, for your labels. I think they were like a 1 and 9, perhaps. Use those. Whatever ringtones had those labels, those are the 2 that got picked. If you start on some different line, you get 2 different numbers. If you get a number repeating, a 4 then a 4, you skip over the second 4 and use the next non-repeating number, like a 3 or a 7. If you got more than 10 but less than 100, you can use labels 00 through 99. Or if you prefer, you can start your labels at 1 and go to 99, but then you wouldn't be able to have more than 99 things in your sample. Very quick summary. We'll talk about that in more detail later. A probability sample is any sample where we use chance or probability to choose the sample. Stratified random sampling, like I just mentioned a minute ago, is a probability sampling technique, but it's based on what are called strata. You take your population, and before you do the sampling, you break it into groups, males and females, by age group, 0 to 10, 10 to 20, 20 to 30, 30 to 40, etc. By state that you live in, Minnesota, Wisconsin, Iowa, North Dakota, South Dakota, New York, California, etc. You're breaking your population into different subgroups before you do random sampling within each group. And sometimes you break it into even more strata. For example, instead of states, you might go into cities within each state. It's more complicated, but it can give you more information. Okay? But it's something you should know about. Undercoverage occurs when some groups in the population are left out. For example, homeless people in a population survey. That can bias your results. All these kinds of things, like the voluntary response sampling, undercoverage, they can bias your results. Non-response, that's similar to voluntary response. Okay, those are the people who don't respond. People who hang up on people, telemarketers, people who want to ask you survey questions, they can result in bias. And bias is bad, not just colloquially in everyday life. You don't want to be biased, but bias is bad in statistics. You've got data, but it doesn't necessarily tell you what you want to know. It doesn't reflect the whole population. Your inferences can be junk, can be worthless. Again, surveys, census, that kind of thing, observational studies, those are passive ways to gather information because there's not much control over the variables of immediate interest. Statistical experiments are active mechanisms for gathering information. In an experiment, we can control for the influence of extraneous variables and focus on potential cause-effect relationships between the explanatory and response variables. This is a business stats course, technically speaking. What's a business situation where you could do an experiment? For example, you could be testing a product. You could be testing it in the factory. For example, testing cars for safety. You've got to do crash tests. That would be an experiment. You're controlling for other factors like temperature, I guess, car speed. You're testing the cars at the same speed, for example. What other things could you control for? Might not affect things much, but maybe a wind speed, that type of thing. Another example is you could test a product and its appeal to customers. Right? Test your product versus your competitors. Make it a blind taste test, for example. That could be an experiment. If you're controlling for other variables, maybe you make the people blindfolded, that type of thing. More terminology. This is related to experiments. Within experimental settings, the terms that we've used so far often have different words, the same idea. Individuals in experiments are often called subjects. Typically, we are thinking about medical experiments here. That's the origin of these terms. So the individuals, for example, in medical experiment are often called subjects. You should know that. Explanatory variables are often called factors in such situations. And treatment is any specified experimental condition, essentially some combination of factors. For example, I'll bring up an example where you're testing plant growth based on how much water you give the plant and how much fertilizer, for example. The watering and the fertilizer are both factors that can affect the growth. Treatment is a combination of how much water and how much fertilizer. And in combination, they can affect the growth. Each treatment can have a certain level. How much water? You can test different amounts. How much fertilizer? You can test different amounts. Different levels. I'm purposely going like this to emphasize that they're levels. More terminology here. So here's that example. You might be testing tomato growth in your home garden. You might choose 4 levels of watering, very small amount of watering, moderate amount, moderate high, and a high amount. You might choose 3 levels of fertilizer, low amount, medium amount, high amount. There would be 12 possible combinations, 4 times 3 treatments. 2 factors, watering and fertilizer with 12 treatments. And you're trying to see what combination produces the best growth. Now, if they're all in the same patch of ground, other variables like amount of sunlight, amount of rain besides the watering, quality of the soil should be approximately the same. So that's a pretty well-controlled experiment. If you were in a greenhouse, you don't want to control for those things. So you got to be careful that those variables don't get confounded. You're focused on the water and the fertilizer. You want to see the effects of those things. I know I'm going fast. We're almost done. It's best if we can assign multiple subjects to each treatment. For example, with the watering and fertilizer for your tomato plants, don't just do it for one tomato plant, do it for a bunch. The same treatment, the same amount of watering, the same amount of fertilizer. Don't just do it for one plant, do it for, say, 10. And then another amount of watering and fertilizer, do it for another 10. Because the effect could be random variation if you're just focused on one particular plant for each treatment. It could be just the particular plant and its genes were bad or good. Okay, so by replicating, you're averaging out the effects, and that gives you better information about what level of watering and fertilizer is best. It eliminates some variability due to chance. In experiments like testing a drug, it's best to do it what's called double blind. The patient shouldn't know whether they're getting the drug or the placebo, and the doctor who evaluates should not know either, because that can bias the results. There's something called the placebo effect, which means even when patients get a placebo, they tend to do better, because it's a psychological thing perhaps. They think they might be getting the drug, so they think they might be getting better. And the doctor might have a bias as well if they know they're getting the drug or the placebo, especially if they have a financial stake, which sometimes they do. Okay? So it's best to do what's called a double-blind experiment in that kind of situation, so that you eliminate that kind of bias. An observed effect so large it would rarely occur by chance is called statistically significant. When you test your new drug, okay, and you want to prove, so to speak, that it does better than a placebo, it better not just do a little bit better. 55% of the people who take your drug do better, and 54% who take a placebo do better, because that could occur just by chance, even if your drug is no better than a placebo. It better be significantly better. Ideally, say 90% for your drug and 10% for a placebo. It's rarely that extreme. But that would be a bigger difference. That would intuitively be what's called more statistically significant, less likely to occur by chance if your drug is no better. So that's some evidence that your drug is better. You get the idea there? That kind of logic is statistical reasoning. And it's the most important kind of logic for us in this course. Chapter 6, we're going to do something called hypothesis testing, where we're doing that exact same kind of logic. What are the chances of seeing this kind of result, even if the drug is no better than the placebo? If it's a small chance, that is evidence that your drug works. If it's a relatively high chance, that's not really evidence that your drug is better than the placebo, even if you got a better result, because it could have occurred by chance. If you'd done a different sample, it might have done worse than the placebo. Okay? Lots of ideas in a short amount of time, and I guess I ended a little early. How about that? Okay, but I know I went over a ton really fast. So I would suggest for sure downloading this and taking notes on it, but maybe also watching some of the video again. Okay? See you next time.